Welcome the new people to the class. Uh, let's see. I'm looking around at everybody that I see on my other screen here. And all right. Let's see, I only have 1, 2, 3, 4, 23 logged in. So, okay. Okay, lesson plan, module 2, radio signals and waves. What is going on here now? Thing is not responding. I had it work. Oh, okay. Here we go. The basic radio station. And the modern one might be slightly different than this, but we have the number one thing, the antenna. The transmitter, a transmit receive switch, and a receiver, and a power supply to power those. Now, in most of the radios that you see nowadays, the transmitter, TR switch, and receiver are all in one box, but they're all there, and they share circuits, and they work very well. Power supply is still somewhat separate. Occasionally, you'll find one that's built in. What happens during radio communications? You have the transmitting that's sending the signal. There's so many different ways you can do this. In amateur radio, you can have voice in amplitude modulation, in single sideband type modulation, in Morse code modulation, in digital format, slow scan television, fast scan television, facsimile. And especially when you get into the digital modes now, there's probably 50 of them or more. And one of the fun things is learning how to experiment with everything in here. The information in electronic form is attached or embedded on a radio wave, which is called a carrier. The radio wave is sent out from the station antenna into space. On the receiving end, the radio carrier with the information is intercepted by the receiving station antenna. The receiver extracts information from the carrier wave, and the information is presented to the user in whatever format that you wish, usually. And this is sound, picture, words on a computer screen, response to a command. Believe it or not, there are frequencies for amateur radio, remote control of model airplanes and things like that really aren't used for anything but that. This, this sounds pretty simple, but in reality, it's pretty complex. This complexity is one thing that makes ham radio fun. Learning about how the radios work, and don't be intimidated. You don't use them all at one time. You're not required to use any of them, and you can use only the ones that you want or choose to use. And as it says, learning a new mode and using it can be fun. I know the first mode I learned was Morse code, and that is one that can be fun to learn. Oh, let's see. Radio waves, electromagnetic radiation, are AC waves. AC stands for alternating current. Radio waves are used to carry the information you want to convey to someone else. And here we start with our wave vocabulary. Before we study radio waves, we need to learn some wave vocabulary. Amplitude, frequency, period, wavelength, and harmonics. Our first drawing here is my pointer on the screen?
Yes.
Okay. The first drawing is of an oscillating radio signal. Waves, the ones you might be most familiar with is if you throw a rock in a lake or a pond and you see waves ripple out from the pond. This is where the displacement of the water causes it to ripple on its way out. When you transmit a radio signal, it works in much the same way. And these waves, in this case, appears they would on an oscilloscope, which is a way to look at what's happening in circuits or on wires visually. And many of the things, the newer things, are displayed on a monitor just like anything else. This oscillation that it represents is a positive and passes through and goes back and forth. The amplitude is the strength or the distance away from that center line. And the amplitude is one of the words we need to think. So this is an amplitude. If we had the same settings on our scope, this would be a signal of lesser amplitude because it would be shorter. The next thing that we need to look at is the period. And the period is from one crossing point to another crossing point of this line. This is one oscillation. And the period, that is about the time it takes for it to do that oscillation. And then the next thing is the frequency, which is how many times that oscillation occurs in 1 second. Our common household current here in the U.S., the frequency at which the power comes into your house is 60 hertz or 60 cycles per second. When you start talking about radio waves, they go much higher in frequency. Wavelength and harmonics. I believe we're going to have some more displays here. Okay. What happens to a magnet when you drop it through a non-ferrous conducting pipe? And it's a lot of fun. And I might show you that a little later. I'd have to go in the other room and get my magnet and my pipe. But take my word for it, it takes a lot longer to fall through the pipe than if you just drop it. And what happens is the moving magnetic field creates an electrical field in that pipe. That electric field creates a magnetic field that opposes the magnetic field of the magnet, which slows its dropping through the pipe. This is much the same way in which radio waves travel. Moving electrons in the antenna create a magnetic field. This changing magnetic field creates an electric field. When the magnetic field collapses is when it creates the electric field. The electric field then builds up during the collapse, and then it collapses. And during the collapse of the electric field, it generates the magnetic field. And this goes on forever. And if you're talking about line of sight and the different kinds of electromagnetic waves, light is an electromagnetic wave. And that you see from stars has been going on for millions of years before it gets here quite often. And that back and forth motion between magnetic and electric fields from point A to point B. Okay. What happens during radio communication? Oops, I have backed all the way up, haven't I? Okay, there are two ways to tell someone where you want to meet them on the radio now. That is frequency and wavelength. And we haven't really discussed wavelength yet, and I guess we better get around to that now. Wavelength is the distance that a radio signal travels in one cycle. And so the relationship between the frequency and the distance is controlled by the speed of light. So you divide the speed of light by the frequency and you will get a wavelength. If you divide by wavelength, you get the frequency. They're reciprocals of each other, and this is the way it works. When they started with wavelengths, it was very difficult in the beginning of radio to measure frequency because they didn't have the equipment that we have now to measure frequency. And they could measure wavelength by stretching two parallel wires out from a transmitting antenna and see the voltage that was induced on those wires and measure it, even with something like a light bulb running down those two bare wires. And when it reached high intensity, until the next high intensity peak is how they would measure the wavelength. So it was simple. So being able to do it like that back in the old days, and it is a carryover to today, a lot of our frequencies or bands that we use are referred to in wavelength. Our original amateur radio bands that we got after World War II were 160 meter band. This is 1.8 to 2 kilohertz. The 80 meter band, which is 3.5 to 4 megahertz. And we're going to have to talk about the metric system here in a few minutes, so it'll be very simple. And then the 40 meter band, and its wavelength is 40 meters, roughly, and it's 7 to 7.3 megahertz. The 20 meter band, which is 14 to 14.35. 15 meter band, which is 21 to 21.45. The 10 meter band, which is 28 to 30 megahertz. And then there's the 6 meter, which is 50 to 54 megahertz. The 2 meter band, which is 144 to 148 megahertz. And I know this is starting to sound like a lot, but that is our relationship. Now, the wavelength at 20 meters, as we said, is 20 meters. And so we're looking at, let me think, 128 feet, somewhere in that neighborhood. Now, the 144 megahertz or 2 meter band we were talking about, the wavelength is 2 meters, which is about 6.5 feet. So you can see that as the frequency goes up, the wavelength goes down. RF radio spectrum. The spectrum is the range of wave frequencies which will leave an antenna and travel through space. The RF spectrum is divided into segments of frequency that basically have unique behavior. Wavelength, the distance a radio wave travels during one cycle. one complete change between the magnetic and electric fields. And I don't know if I mentioned it, but for radio purposes, we use the speed of light as a rounded off number, which is 300 million meters per second. That's a whole lot easier to remember than 186,000 miles per second. And believe me, the math is much, much simpler. Now, they have divided the radio RF spectrum into, as they say, bands that kind of behave the same. For instance, in this case, and we'll go through it, the very low frequency VLF band is 3 kilohertz to 30 kilohertz. 30 kilohertz. Most of this is in the actual audio range that you could hear it if it was a signal that way and you ran it into a speaker. Then low frequency is 30 kilohertz to 300 kilohertz. Medium frequency is 300 kilohertz to 3 megahertz. That's where your AM broadcast band falls in that you may be familiar with, like here in Western North Carolina, WWNC, WSKY. Those stations are on. And then we get, for amateur radio operators or me, the high frequency, which is 3 megahertz to 30 megahertz. And this is where you get your long distance fine communications. This is where you talk to people all the way around the world. And it is, in my opinion, one of our most useful spectrum pieces that we can use. Then there's VHF, which is 30 to 300 megahertz. And we have 3 ham bands that fall in there, which is the 6 meter, the 2 meter, and the 220 megahertz, which is 1.25 meters. And those are mainly line of sight. Your TV transmissions used to fall in that range before they changed to the digital TV. And then we have the UHF. And this really becomes a line of sight phenomena in these frequencies. And your antenna elements get very much smaller in the 300 megahertz to 3 gigahertz, which is 3,000 megahertz range. And then you have super high frequencies, which is 3 gigahertz to 30 gigahertz. And then you get the extremely high frequencies. And up in those is where you have a lot of your radars and things like that. More than amateur radio things, but there are amateur radio things that go on. Just out as fun, I'm going to show you an antenna. Let's see. Do you have a screen that you see me in also as well as that in the view section? I'll show you this antenna later.
Yes.
Did you see it?
Oh, no. Yes, I could see you. It's a little bit small, but yes.
Well, that little antenna that I'm holding there is for the ham band 1.2 gigahertz. Just to show you that as your wavelength gets smaller, so do your, as your wavelength gets smaller, so do your antennas. And that covers the spectrum. And now, these are the questions that will be on the exam. What is the name for the distance a radio wave travels during one complete cycle? In this case, it's a wavelength because you're looking, if you look at this, it's kind of giveaway because you're looking for a distance. The only one that it even refers to in there is a length, and that's a wavelength. It's not a wave spread or a waveform or a wave speed. Although, get back to this, the wave speed is always 300 million meters per second. How fast how fast does a radio wave travel through free space? In this case, at the speed of light, it's A. C says the speed is inversely proportional to its wavelength. That's true, but it doesn't tell you what it is, what that speed is. And as the speed increases, as the frequency decreases, no, that's not true at all. And the speed of sound is a lot slower than the speed of light, somewhere in the neighborhood of 700 miles an hour. How fast does a radio wave? Well, come on. Oh, it's coming up with the answer. How does the wavelength of a radio wave relate to its frequency? And that's going to be B. The wavelength gets shorter as the frequency increases. What is the formula for converting frequency to wavelength? Wavelength in meters equals 300 divided by its frequency in megahertz. What properties of radio waves is often used to identify the different frequency bands? And I believe that's the approximate wavelength. What are the frequency limits of the VHF spectrum? And I admit some of this stuff you just kind of have to memorize until you get where it's used often enough to know it, but that's 30 to 300 megahertz. B. What are the frequency limits of the UHF spectrum? That would be 300 to 3,000 megahertz. What frequency range is referred to as HF? That is 3 to 30 megahertz. One thing I will say is when they named these different frequency bands, and when they first gave amateur radio frequencies, they considered 3 to 30 to be a very high frequency and useless. So if you have to think is when they named these things was in the neighborhood of 100 years ago, and they suspected that some of these things nobody'd ever be able to use, and they were wrong. What is the approximately velocity of a radio wave as it travels through free space? And that would be, boy, I got two D's there, but it's the first D, 300 million meters per second, which is 3 followed by 8 zeros. What is the unit of frequency? And it was named, the unit was named after a fellow whose birthday was last week, and his name's Heinrich Hertz. And it is the Hertz. And when I started in amateur radio, we did not use that term. So it just goes to show you I've been a ham a long time. What is the abbreviation that refers to radio frequency signals of all types? In this case, it is C, RF, which stands for radio frequency. So where am I? Back to how to tell where you are in the spectrum. Bands identify the segments of a spectrum where you will operate. Wavelength is used to identify the band. Frequencies identify specifically where you are within the band. No one ever refers to a wavelength down to fractions of an inch kind of thing, whereas frequencies, what you can get down to one cycle or less, or 1 hertz or less, and it's much more precise in your measurement. For the station antenna to efficiently send a radio wave out into space, the antenna must be designed for the specific operating frequency. The antenna length needs to closely match the wavelength of the frequency to be used. Any mismatch between antenna length and frequency wavelength will result in radio frequency energy being reflected back to the transmitter, not going or being emitted into space. And that's what they call a standing wave ratio. When we imprint some information on the radio wave, we modulate the wave, turn the wave on and off with voice, AM, FM, data. Different modulation techniques are called modes. CW Morse code is on and off code. They call the short sound a dit, the long sound a da. Technically, the da is supposed to be 3 times the length of the dit, and it's done with what they have right there in the middle of the picture, a key, if you're sending by hand, and it actually turns the switch off and on when you mash the handle down on the key. AM is amplitude modulation. This is where they impress the audio AM wave. Amplitude of the wave is impressed upon the carrier wave in step with the sound of the information or the voice. AM signals consist of 3 components. The carrier wave, which, again, if you can see my pointer, is right here in the middle. Upper and lower side band. Voice bandwidth is from 300 hertz to 3 kilohertz. AM bandwidth is twice the voice bandwidth. Sound waves that make up your voice are complex mixtures of multiple frequencies. When this complex mixture is embedded on a carrier, 2 sidebands are created that are mirror images. Since voice is made up of identical mirror image sidebands, we can improve efficiency of the transmission by transmitting only 1 sideband and then reconstructing the missing sideband in the receiver and the carrier wave. Frequency modulation. Instead of varying amplitude, if we vary frequency in step with the information waveform, FM is produced. The FM signals are much more resistant to the effects of noise, but require more bandwidth. FM bandwidth for voice is between 5 and 15 kilohertz. And if you look at our drawings here, you will notice that the amplitude of these oscillations changes. It gets narrower and wider. And this is what they talk about, frequency modulations. That actually changes the frequency of the carrier to impress the voice on it. Why should you not set your transmit frequency to be exactly at the edge of an amateur band or subband? To allow for a calibration error in the transmitter frequency display, so that modulation sidebands do not extend beyond the band edge, and to allow for frequency drift in your transmitter. And the answer is all of these choices are correct. Any of which could get you outside of your allotted band of frequencies. What determines the amount of deviation of an FM signal? Both the frequency and amplitude of the modulating signal, the frequency of the modulating signal, the amplitude of the modulating signal, the relative phase of the modulating signal and carrier, the amplitude of the modulating signal. What happens when the deviation of an FM transmitter is increased? Its signal occupies more bandwidth, its output power increases, the output power of the bandwidth increases, asymmetric modulation occurs. Its signal occupies more bandwidth. Which of the following is a form of amplitude modulation? Spread spectrum, packet radio, single sideband, phase shift keying. C, single sideband. What type of modulation is most commonly used for VHF packet radio transmission? That would be FM. And packet mostly occurs, I believe, on 2 meters. Which type of voice modulation is often used for long distance or weak signal contacts on the VHF and UHF bands? I believe that would be single sideband, SSB. What type of modulation is most commonly used for VHF and UHF voice repeaters? And that is DFM. Which of the following types of emission has the narrowest bandwidth? FM voice, single sideband voice, CW, or slow scan TV? That would be CW. Which single sideband is normally used for 10-meter VHF and UHF single sideband communications? And that is upper sideband. What is the primary advantage of single sideband over FM for voice transmission? SSB signals have a narrower bandwidth. What is the approximate bandwidth of a single sideband voice signal? That would be B, 3 kilohertz. What is the approximate bandwidth of a VHF repeater FM phone signal? Between 5 and 15 kilohertz. What's the typical bandwidth of analog fast scan TV transmissions on the 70 centimeter band. And I think that's B, about 6 megahertz. What is the approximate maximum bandwidth required to transmit a CW signal? CW signal, 150 hertz. This means you can get a whole lot more CW signals onto the band than you can sideband or voice. Okay, so evidently I've gone through that demonstration. Let me try something else over here.
And I want to add, guys, this is starting off probably to a lot of you is very, very confusing. But as the class goes along, all this will start coming together and you'll get a better grasp of what we're talking about when we're teaching you this. So don't get discouraged because some of it's over your head, but it will come to you. Trust me.
All right. Now this screen that we're looking at is the 80 meter band. Can everyone see this display?
Yep, you got it.
Okay.
You're looking at FT8, I think.
Well, what we're looking at is a portion of the 80 meter band, and we can look at a few different kinds of signals here. Well, I'll use these cross things. This signal here is a Morse code or CW signal, where you can see it turning on and off quickly. Let me come on. I can't see my volume control to turn that off. I have something in the way here. Yeah. But at any rate, this is a CW signal. In this area right here, we're looking at the highlighted area, and here's 3 kilohertz, and there are quite a few FT8, which is a digital mode, signals right in that area. And they are probably as close to as narrow as CW, which you can see these here. Now we're going to go up into the upper end of the band here.
Just for a comment there, I'm seeing 9 signals on my screen now on 80 meters on FT8, and that's really a small number. It could be over a dozen, and your computer will hear all of them and decode all of them. Whereas if you were listening to 12 different people talk on the radio, Chris is shaking his head no. He's correct.
I just can't get up there to turn the volume on because this meeting is being recorded. Okay. Does it? I need to hide this bar or move it somewhere if I can. There we go. Okay. I hope you can hear that. And we're going to change the type of modulation that we're using here. Since this is 80 meters, this is lower sideband. And this is lower sideband. Where you see the line here would be where the carrier wave should be, and if you had an AM signal. Now we'll go up to a different band.
Yeah, Howard, we didn't hear anything there.
Oh, you can't hear anything? Okay, sorry about that.
Hey, Howard, if you stop sharing for a second and then reshare and check the box that says share sound, it should send the sound from your speakers out through the Zoom as well.
Okay, let me see what I can do.
If you want to hear FT8, I've got it running on a radio right now.
Yeah. Well, what I can do. Can you hear it now? Hello.
We hear you, but not the radio.
All right. We'll move right along quickly here. Let me go up to now this is the AM broadcast band. And so these are AM signals. And what we were looking at, this spike in the middle of all these signals, these are different stations, is the carrier wave with the right-hand portion here that you see, and then the left-hand portion, the right hand is the higher frequency, so it's the upper sideband of an AM signal, and this is the lower sideband of an AM signal, and you can see that it would therefore be very, very wide. When you talk about a sideband, they filter or phase, there's several different ways of doing it, out the carrier and one of the sidebands. Let me go up now to as Harry was talking about, 20 meters is usually a very busy band. And you can see how many different signals are going on in that portion of the band right there. And that is your FTA signals. Let me see if I can get up here into the upper sideband portion. Okay, these are upper sideband signals. I don't see anything really strong here right now. I need to, yeah, upper sideband.
Yeah, there's a bunch on that 20-meter FT8.
Yeah. Sometimes you'll see 20 or up on there. Here's a good upper sideband signal. And this is a single voice signal. And the width here that I'm receiving in that case is 2.7 kilohertz. We'll change it up to 2.9 so that you can see how wide that signal is. In that same space, you can have 20 or more of the digital signals operating at the same time. Randy, can you get on 6 meters?
Howard, there's a net going on 7.244 right now. If you want to go up to 40 meters.
How about 6 meters? I want to see an FM signal.
I can give you a CQ on 6 meters on FT8.
I don't want FT8, I want an FM signal.
Okay. Can't do that.
Yeah. I know Randy operates FM on 6. It's what your nets are.
How about 53,130?
All right, let me get up there. All right, make a transmission when you can.
Kilo India 4, Victor Lima Whiskey, testing. 1, 2, 3, 4, testing. 1, 2, 3, 4.
I had you, but I'm zooming in, so I do it again.
Okay, you need to go back to 53, Howard.
Went the
Okay,
wrong way.
okay. You ready?
Yeah,
Kilo India 4, Victor Lima Whiskey, testing. 1, 2, 3, 4, testing. 1, 2, 3, 4. It keeps dropping down to 50.
what?
I'm on 53.
Hold on just a second. That's where I missed it. 53,130.
53,130.
I hear you coming through loud and clear on my station, Randy.
All right, now let me change this thing to FM. All right, Randy, just
You
try
ready?
again.
All right. Kilo India 4, Victor Lima Whiskey. Testing. 1, 2, 3, 4. Testing. 1, 2, 3, 4.
And that's what an FM signal looks like. You can see in the time domain down here on the bottom, the signal slowly sinking off the screen. So that's several different types of modulation off the bat to show you what they look like on this is a fairly modern digital receiver. Okay, I need to stop sharing. Here we go. Now, band module 3. Radio equipment basics. And the basic radio station, a transmitter, TR switch, and receiver. station equipment, receiver, transmitter, antenna, and a power supply. We were on that when we started. Now, how we got off, I don't know. Repeaters are automated stations located at high places that receive, then retransmit your signal simultaneously, dramatically improving the range.
Howard,
Yes, go ahead.
the screen is not, at least not on mine. I'm only seeing the right half of your screen. Anybody else the same way?
Yep, it's cutting off the left-hand edge of the slide. I don't know if you can center the slide in your shared screen.
I do not know what is doing that. Like right now, you're seeing, I see a green line on mine that must be something that's doing it.
Yeah, because
Let
on this one, we're seeing the picture like it's supposed to be.
Okay. Time I turn around. Accessory equipment.
It looks okay. Now your letters are chopped off, but your pictures are right. Well,
No.
pictures are small enough that you can see all of them. That's what it's doing.
That make a difference?
No, it's still the same thing. Zach, do you have any idea what's causing that?
Sorry, I didn't quite catch that. I'm actually working on some stuff here. What's the issue there?
When he goes to show his screen, it only shows half of it.
Did he hit whole screen or just click on the PowerPoint window?
I don't know.
What are you seeing now?
Oh, that's
your
presenter view.
Yeah,
You may need to pick
the other screen.
Yeah, that's what I was just about to say.
Oh, wrong button. That look better?
Yes.
Okay. And we're talking about repeaters. The basic components of a repeater are the same as your station: a receiver, a transmitter, antenna, and power supply. But repeaters are transmitting and receiving at the same time using the same antenna. This requires a very high quality and special filter to prevent the transmitted signal from overpowering the receiver. This specialized filter is called a duplexer. And here's a drawing of a repeater, and you will see that the received signal goes from the receiver into the transmitter and then is retransmitted on a slightly different frequency. Basic station accessories. Human interface accessories: microphones, speakers, earphones, computer, Morse code key of some type, TV camera, and kind of whatever you're interested in using with your radio. Station performance accessories are an antenna, SWR meter, which is an antenna match checker, an amplifier, antenna rotator, filters, etc. And this shows accessory equipment connected with your transceiver. What? I have a bar here that's always in my way. What type of amateur station simultaneously retransmits a signal of another amateur station on a different channel or channels? And it's C, the repeater station. What could be used in place of a regular speaker to help you copy signals in a noisy area? C, a set of headphones. Figure T5 represents a transceiver in which block 1 is the transmitter portion and block 3 is the receiver portion. What is the function of block 2? And that's your transmit receive switch. And again, those are questions that are possible to be on the examination. Now, I think I have covered a good bit of it. It seemed, I thought I had something I had to talk about the metric system a little. And I didn't think I had another module I needed to use, but let me check real quickly. Let's back up while I'm doing that. Does anyone have any questions about what we've been talking about? I know it kind of seems to be a lot in a very short amount of time.
One comment I'll make is, at least I noticed in the first module in college, I had a professor. First exam we had in the semester, student asked him, says, "What's going to be on the test?" And the professor's answer, and it applies here too, what's going to be on the test or what's in this course is going to be covered in your book, on the test, and in the final exam. I noticed some of the questions that you were asked were not in the presentation. They are in your book, which basically means you got to read the book and watch us.
And I will add some of this that Howard has gone over tonight. Later on, with some of the other classes, we're going to go into a lot more detail, such as repeaters, contacts, and things like that. So, like I said before, this is just a build up to carry you along through the other chapters in the book. So that will be coming, and we take it slow and easy, and hopefully give y'all time enough to absorb a lot of this. But if any of you guys have any questions at any time, please let us know.
Hey there. This is Christina Vizcaino. I wanted to ask a question about something that you said earlier, where you said as your wavelength gets smaller, so smaller wavelength, higher frequency, your antennas also get smaller. Is that what you said?
Yes.
Okay.
Uh, and I'll be covering antennas not next week, but the week after. But
Okay.
in generally speaking, and I will just talk to one type of antenna, which is a dipole. And the dipoles that we use are meaning two poles, and it's a wire with the power set fed into the center. And we hang up in the air between trees or towers or whatever's handy. And they work very well when they are a half wavelength long. So a 40-meter dipole is roughly 20 meters long. Does that make sense?
I'm just gonna write it down and let it sink in later. I'm admitted I'm also a little lost, but I'm gonna plan to uh watch the recording again.
All right, but again, the key to this is the formula, which you can write down. And the formula is, and we'll give you three. Frequency equals the speed of light, which is 300 million meters per second, divided by the frequency, in that case, in cycles. As a shortcut, they just use the number 300 divided by the frequency in millions of hertz, which is megahertz. So, say the 40-meter band comes off of 7 megahertz, so it'd be 300 divided by 7. If it was actually 7.5, it would come out, I think, to exactly 4. Does that make sense now?
Yes, thank you.
And to relate that further, uh, that is the wavelength for the frequency. You can divide 300 by the wavelength and get the frequency. And therefore, I think you can multiply the wavelength times the frequency and get the speed of light.
And for right now in your learning process, don't let any of that worry you. Keep in mind when you look in the question pool, what kind of questions they're asking you. And that's what you need to concentrate on right now. There's a lot of knowledge that you're going to hear us talk about that you're going to have to be like a sponge. You're going to soak it up, and then one day you're going to squeeze yourself and get the right answer out, but it won't be today.
Can I break in on this?
Of course.
Howard, all your information that you're giving is on page 2-6 of the manual.
Okay, let me. I got you. And I finally got into where I need to be over here. But I think we have probably covered most of it. I know that there's a thing in there where it talks about that I think I really need to talk about the metric system a little bit. And really, this prefixes that are used with whatever is being measured. And I guess the most common one is, your a meter and a kilometer, which is a meter and 6,000 and a thousand meters, and that's a kilo. And a kilometer means 1,000 times a meter. And kilo is one that we use in radio, and instead of saying a big old long number, we will say 1 kilohertz instead of saying 1,000 cycles per second or something like that. And they mean the same thing. Mega is a million, and mega is used quite often because kilohertz, we're usually talking almost audio when we're talking that. There's a few radio bands that we can use that are in the kilohertz range, but most of them are in the neighborhood of the really ones that we use most often start at 1.8 megahertz or 1,800 kilohertz, if you wanted to say it that way, and go up. And then there's the giga, and you heard of, a memory, a memory being a giga memory. And then you hear of a tenth of a meter being a decameter. Well, we don't use that prefix much in radio. But the next one down is a doggone. A deca, 100th is a 100th. Help me, Harry.
How about a decimeter?
Yeah, a decimeter is a tenth of a meter. And obviously, this can get you confused a little bit.
And a centimeter is 100th of a meter.
Yeah.
Is 100th of a meter, and a micrometer is 1,000th of a meter.
You mean a millimeter?
A millimeter, well, okay, a millimeter, yeah.
And then I think micro is a 10,000th. I don't know what gets fuzzy past that.
That's what I'm thinking. But these are all prefix terms that you'll get used to, and it's not something that you have to worry about. It's just like when you're looking at a memory in your computer and you say, we got a terabyte in here, and we got a gigabyte in here, and we got a kilobyte in here. You realize that a megabyte is bigger than a kilowatt. Megacycles are higher in frequency than kilocycles, and it's just terms that you'll get used to. And we don't do an awful lot of real math much. There are, I guess, a few formulas and derivation and the derivations thereof that we use in amateur radio a good bit. And the one that I just gave you about wavelength and frequency, whereas the frequency, to get the frequency, you divide 300 million by the wavelength in meters. If you want the wavelength, you divide 300 meters by the frequency in megahertz. And that just makes it math simpler by dropping those 6 digits on the right of both those numbers off out of your way. And that is one that you use when you're thinking about antennas a lot. I think, let me see. Yeah. I'm going to hold this up again. I know this is hard to see. Are you looking at my picture where you can see that?
Yeah.
That is a 1.2 gigahertz ground plane antenna. And so its wavelength is 4 times this long, but about like that. Whereas if I had an 80-meter version of that, the vertical part would be 128 feet long, and each of the things sticking off the side would again be 128 feet. This is the highest frequency hand band that I have to operate. But the antennas get smaller, and because of that, you can get make antennas that have higher gain, which means they make the signal strong. And that's one thing where a lot of people that have been in CD radio have a tendency to go toward amplifiers and stuff. But antennas assist you in both receive and transmit. And in my opinion, the antenna is probably more important than the amplifier. Says the guy who's putting up his first tower and antennas like that after many years. There's what I've been trying to get to. But that's
Howard?
yes, go ahead.
Yeah, on the chat there was somebody was confused a little bit between CW and single sideband. And another question was CW is Morse code, and the two are tied together, but CW is a means of modulation. Morse code is a, I guess I would say, digital language that we can send with CW. And so when you use Morse code, you use CW to send it, which means that we are turning the carrier on and off. We're not modulating it other than turning it on and off. So that's the CW part. Morse code is the pattern we use to turn it on and off. So does that explain the CW and Morse code to the question? And then the other one was single sideband and CW. They was a little confused on that. You want to go into that a little more?
Yeah, we'll go into that a little. In the beginning, Morse code was the only method of modulating a radio. And so when you hear about Marconi and his sending a signal across the Atlantic, it was a big deal. And what he sent was the beginnings of Morse code. And those codes originated with the telegraph system. They've changed just a little bit, but Morse code is what people were using to send a telegraph signal where they were just turning something on and off the same way. So it was natural when they started experimenting with radio to learn to be able to turn it on and off. Then I can't remember who it was, whether it's Armstrong or one of them, that came up with the idea that they could impress an audio signal onto the carrier wave. And the carrier wave is the basic signal that carries your transmission back and forth. And that when you make the difference in the carrier wave is how you transmit that information. If you just turn that carrier wave on and off, you get CW or Morse code. Once they impressed the voice onto that carrier wave, it became amplitude modulation. And amplitude modulation, that came in the very early, about 100 years ago, in the early 1920s. And that went on pretty well for quite a while. Then somebody figured out that if they filtered out part of the signal, they could take out the carrier and one of the sidebands, and they could put all their power into just one sideband. And then to be able to receive that, you needed a carrier wave, but they could generate an oscillator or a frequency inside the radio that would regenerate that carrier wave as far as, and just impress that one sideband on it. And you could tune that, and the advantage to it was it had about more than half, again, the power, because it wasn't transmitting the carrier, and it wasn't transmitting the other sideband. And so it was much more efficient, and it used up, because of this, it was also narrower in frequency that it was using. And it probably came in the 1950s, but you didn't see it much until the 1960s in amateur radio. Personally, somewhere around 66 or 67 is when I saw enough sideband activity to begin using it, because I had to convince my parents that I needed a sideband radio, and that was so we're talking about a very long time ago. FM came in, I think in the 30s, and that may have been Armstrong that invented FM. And a lot of the things that we use, like I do VHF contesting, and you do use upper sideband because it uses a narrower signal. Now, let me talk about noise. Noise is something that gets into your radio, and it comes from everywhere, outer space and everywhere else. And what you worry about a lot in your receiver is the signal to noise ratio. The more signal that you can get in to the portion of band that you're listening to, the better you hear it, because there's always some noise there. And I know if you've noticed, tuning between stations is where in the radio is where you really just hear noise. But when you're trying to hear a really weak signal, the narrower his transmission, you can use filters to where you're listening to a smaller and smaller portion of the frequency band, so that you can make your signal to noise ratio better, so that you can better hear it. I noticed this, and the way they do it is there's several ways of doing it. Nowadays with the computers, they do it with math. We have done it in the past with crystal filters and things like that, but it's pretty common to think that the narrower the bandwidth of a signal, the easier it is to hear a weak signal. And that's just where the signal to noise came into. And I have done everything I need, because I brought up module 4, and that's going to be the next class for me, I guess.
Let me make a comment here. You will hear us talk about things, and some of us will. Okay, and this is a perfect example. The 70 centimeter band. Okay. We've talked about the 80 meter band. You go up to the 70 centimeter band. You will very seldom hear any of us talk about our 70 centimeter handheld radio. 70 centimeters is somewhere in the vicinity of 440 megahertz. And so we're going to really mess with I'm going to mess with your mind right now. My handheld radio is a 2-meter 440 radio. Okay, what I have just told you is that on one band, I am telling you that it receives a signal that is 2 meters long. That's my 2-meter handheld. That's somewhere in the vicinity of 144 to 148 megahertz. Okay, but you will never hear me talk about my 144 megahertz radio. Now, the other end is you will very seldom hear me talk about my 70 centimeter radio, but I will talk about my 440 megahertz radio, except I won't say megahertz. And for those of you who are not familiar with the jargon, I can see why that would confuse you. And my only word of wisdom is that the longer you listen to us talk to each other, the more confused you may become. Don't let that bother you. You'll catch on. And I think part of it is just how we learn to talk to each other. And again, I think 440 is a whole lot easier to say than 70 centimeters. And I think 2 meters is a whole lot easier to say than 146.910 megahertz. And that's just the way we talk. We're saying the same thing, which I think Howard did a pretty good job of, number one, confusing you and also explaining it too, when he explained how you could divide the speed of light by either frequency or wavelength and get the other one. We're sort of doing the same thing when we talk. So again, don't let that, number one, don't let it confuse you. And even more than that, don't let it discourage you, like these guys don't know what they're talking about. And you're probably right there too. But don't let that slow you down in learning. It will come to you. And Joe's sitting up there. He's kind of new at this, but he's an OCBer, and he never talked about working. What was it? 27 megahertz or the 12-meter band?
11 meters.
11 meter, yeah.
That was always a sore spot for the amateur radios, but because they took it away from amateur radio operators and made the 11-meter band.
But you never hear us talk about the frequency. It's always 11 meters. And again, that's just the way we talk about it. They mean the same thing.
Yes.
I don't know if I've confused you or muddied your water to the point to where you can't even see it, or.
And the one thing I will say is, I know it sounds confusing, and I can even get confused. We use numbers like pico, but we only use those when you're talking about a capacitor. When you're learning about component parts, you start learning about the kilos and the megas and all that again. But at the time, they will make more sense to you when you get it. Right now, you just need to know that when we talk about frequencies, we talk about kilometers or kilocycles or kilohertz. And when we're talking about wavelengths, we're talking about meters. If you get into the kilometers, those antennas are just too big to think about.
And guys, what you can do to help out, Chapter 6 of your book, this, if you can see it, should be in there. Okay, this is the band plan. That'll be in Chapter 6. If you got a printer and can print this off, do so, because that'll help explain some of this right there. So I believe it is in Chapter 6, and we'll be going over this later on in the class. But that'll give you a jump start understanding some of this.
And the numbers, the prefixes that we use, and as it says in the book, the M is always capitalized when you're talking about megahertz, and the G is always capitalized when you're talking about gigahertz and stuff like that. But these are just make it a simpler way than giving you a I'm going to meet you on 3.502763. And that is a ham frequency. But we'll probably round it off if we're going to say, I'm going to meet you at 3.520. And most of your receivers are wide enough that once you get there, you're going to hear that other 700, is close enough to hear it. So it'll get you in the neighborhood. They're just to keep you from using big, long numbers. Does that make sense, Harry?
Yeah, think about, I need a 20 picofarad capacitor. That is a point, and you count my zeros and see if I get it right. 0, 0, 0, 0, 0, 0, 0, 0, 0. Is that enough zeros?
I think you need 2 more.
Okay, 0, 0, 20. Would it be easier to say that, or was it say, give me a 20 picofarad capacitor? That's what we're saying.
And these numbers are actually multiples of 10 is what they are. They just have a name. I know that I had a fellow watch one of our classes that were telling me jumping into this math off the bat was just too rough. And I'm trying to say it's not that important now. When you get around to actually use it, you'll understand it better. But they're just numbers, and it's a shorter way of saying a lot of them.
Yeah.
The math that we use is, until you get into some really freaky stuff, is really simple, just multiplication and division. Another one that you're going to learn is Ohm's law, and there's about 2 of them. One's and it's just multiplication and division. And we teach it to you. We draw a circle, and with our wavelength and frequency, you could draw a circle, and then you draw a line right through the middle of that circle. In the top half of that circle, you write the number 300. And then the bottom half of that circle, you divide it again so that you've got 2 quarters down there. And in one of those quarters, you put frequency. In this case, you could put down in MHz for megahertz. And in the other one, you put wavelength. And that could be shortened to just meters. And you say, I need to know that for me. You just covered up one with your finger that you want to answer for. And the formula's like there. You cover up frequency and it says 300 divided by length in meters. If you want to know the frequency, it's 300 divided by, like say the length in meters. If you want to know the wavelength, you cover up the wavelength, is 300 divided by the frequency in megahertz. Again, megahertz, it just means that you got your first number followed by 6 more numbers. Have I got everybody confused enough? Oh gosh, what time is it? About 22. Now, seriously, any questions along any line, please speak up. I know I teach 2 of these lessons, but at any time during this, because maybe they're my favorite thing, and the next one is really my favorite one, which is antennas. Antennas are the one thing that hams all need to use. They can be just very simple, or they can be very complex. So, and the truth being, a lot of hams, they just come out and tell you, I want to operate 20 meters, and the guy will tell you, here, I'll show you an antenna. Or I can tell you how to build the antenna. Either way, Harry likes to build them too, don't you, Harry?
Yep.
Howard, does that mean I'm up next week?
You're up next week. Want to
Okay.
give them a preview? Tell them to read?
If they're not confused enough now, they will be a week from now.
And just to throw out a little bit of stickler here, while you guys were talking, my computer just worked Malawi on 20 meters FT8. That's in Africa.
You had
Yeah.
you had the privilege of being able to just listen.
And I just made a contact in Michigan on 40 meters. Guy was calling CQ.
It's all fun, folks.
Yep.
And we love our
Yeah.
radio. I guess we can bail out a little early if we don't have any more questions or anything else to confuse you with.
Well, Howard, I just want to tell everybody, if you look in the chat, I just put the band plan there, so you can download the band plan from the chat and have it on your computer without having to go hunt for it. Everybody know how to use the chat?
I don't
think
think I
you-
see the document in there. I'm in the chat though.
It says band plan, 8.5
Anyone
by
else
11
see it?
color. It's in a PDF file. It's to everyone. Maybe I didn't hit return. That's it. There you
There you
go.
Yep,
Sorry
there you
about
go.
that.
Thank you.
Gotta hit return.
I haven't been going through the chat while I was talking, and I saw it says a lot of this seems to be missing in the book. And I guess we are actually covering more than you absolutely have to know to pass the test. And we're trying to give you a little bit more, and especially when we start getting around to Randy, we try to get to the point where you're going to be comfortable using the radio when you pick up that microphone of yours for the first time. That's what we want to do, is not only see you get a test, we want to talk to you on the air.
Now, there's two things to keep in mind here. Number one, and you can reverse this around to what you think is more important, but there's two things that go on here. Number one, in order to join this fund, you have to pass the test. And the test is not covering everything we talk about. But number two is we would really like for you to learn. And learning, to me at least, is where the fun is. Or I've got sitting over here a 40-year-old radio. I was about ready to take it to a Hamfest flea market and sell it, because my other two radios right now are hooked up to a computer. That radio doesn't even have an RS-232. Now, some of you are old enough to know what that is. Some of you think that the only thing is now a USB-C connector. But that radio doesn't even have they didn't know what computers were when it was designed. And I read an article on how to interface that radio with my computer. And if I turn it on right now and turn the computer on, I can get on FT8 just like I have my 7300 that you can see in the background. It's a state-of-the-art radio, and the only connection between it and the computer is a USB cable. And I can change the frequency with the computer. I can change the frequency by turning the knob on the radio, and the computer keeps up with it. But that's just all part of learning. And to me, that's the fun part. But going back to the first thing is study the questions and learn the answers. And again, there are some online tests that you can practice taking. They are the same questions that if you, wherever you go to take your test, they're going to give you a test. Those questions come out of that question pool.
And you might want to add too, when you do go take your test, there's 10 to 12 variations of the test. And the tester, the guy in charge, has one test of each. So he won't know which one he's handing you. So when you go take the practice test, make sure you take all variations, all 10 or 11 of them. That's important.
Well, if you use one of those websites, every time you bring up a test, it will be different.
Yeah.
And a little rule of thumb is if you're studying and if you're taking those tests, when you're getting like 85% complete consistently, you're ready to take the test. You've got enough knowledge at that level.
Mm-hmm.
Now, when you start studying for the next license class, you're going to find out you don't know anything. Oh, we get a whole lot deeper in the technology at general, and then extra class lets you know that when you got your general, you still don't know anything. And then after you get your extra, you're going to look back and say, I still don't know anything. So it's all fun learning.
And we will encourage you also, once you get your license, get on the air and use your radio, because that's going to be important. That's where you're going to learn, is once you get your license, get on the radio, start making contacts. Everything will come together, and you will learn even more then. And this is just preparing you to get the license and get on the radio. And when you get on the radio, you will learn a lot more.
Yes. Well, I can remember when I made my first contact, went through a class just like you're doing right now, except we did it in a classroom, met once a week, and I took my test, passed it. And back then we didn't have the computer, so they had to mail the stuff into the FCC. And I went home every day at lunch for about a month to check the mail. And finally I got the letter that had my license in it. Went back to work, and a couple of my coworkers were licensed hams. They were part of encouraging me to do this. And one of them gave me his radio to take home. And I'm sitting on my front porch, and I turned it on and was listening to one of the local repeaters, and one of the other hams who had been teaching the classes was talking to somebody. And I'm sitting there, and literally my hands shaking, my voice quivered, and there's sweat running down my brow because I was afraid to mash that button on the side of the radio. Now, most of these guys here that know me won't believe that that day ever existed. But I got over it. Right, Chris?
Yep.
And it's been fun ever since. And one thing I would encourage you to do, after you get your license, get a little bit of practice. When somebody says, hey, would you like to help teach a class? Take it, because when you start teaching, that's when you really learn. I mean, because when you're teaching somebody else, you tend to be maybe a little more careful, like not talking about a 2-meter 440 radio in front of brand new people that don't know what that means. Oh, it helps you learn. That's also a way to give back. See, I can quit.
Okay. This is, guys, I'm going to turn this up. This is that ham I talked to in Michigan on 40 meters.
Understand it.
Pleasure to meet you today, David. You got Zach and you Alpha Charlie Hotel up here in Michigan, just west of Detroit. Over.
So that's two guys talking on 40 meters. One's in Michigan, sound like the other one's in Maryland. And we'll go over this too with the phonetics and all this kind of stuff too. But basically, that's it. It's once you get into it, believe it or not, it's not bad. It's very simple. Just a few things to learn and remember. And, you know, and just remember, and I'll go over this again too, probably say it 4 or 5 times, but we all here started where you guys are at now. So just remember that. We went through it too, what y'all are going through.
When I learned my first contact, I'm sure my hand was shaking, and I'm not sure the guy could copy the Morse code I was having to send on my first transmission.
Yeah, we all get nervous.
Yeah, we all get nervous. Back then, I was somewhere in the neighborhood of 14, 15 years old, and you can imagine really being scared to death of messing with one of these pieces of equipment and learning, and it's been a great influence in my life ever since. And I will say so that there's enough stuff in this to keep you interested more than 60 years. I know that.
Yeah. I've
lived it.
And some of you will be afraid of making a mistake once you get on the radio. You're going to make a mistake. Hey, I still make a mistake from time to time, but, you know, doesn't bother me. We all do. But don't worry about making a mistake. It's okay. Just learn from it. And, you know, and my wife, she's got her license. She doesn't get on the radio that often. She needs to get on there more because Harry and all of them can tell you she's got a better voice on the radio than I do. And she's more understandable on the radio than I am. And, but when she gets on there, you know, she does a great job. Any other questions?
Well, we're about 8 minutes but before 9. I'm happy to have everyone. Please hang in there. We'll try not to confuse you. Read your book again. Study for next week. And when you're looking at it, if you have a question, I think my email address is at the top of everybody's link that I send. I'll send out another one next week to everyone, just in case you happen to have lost the link to the Zoom class. I'm not really good at answering emails like that, but, you know, we might even get a telephone call going if there's something you want to learn. So, have a good one. I think we'll call this the end of it. So 73s, which is again, came from Morse code, da 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 da. Best regards.
And I'll throw one at you. I'm gonna go QRT.
When you contact people in foreign countries and you say, how can you talk to somebody in Japan? One thing that we have had for about the length of ham radio is something called Q signal. And if he says QRT, that means he's going off the air. And if you send that in Morse code, doesn't matter what language the guy speaks, he's going to understand. Yeah. QTH is where you live. What's your QTH? So I'm sure you'll learn those, but it's not anything you need for the test. So You'll get around to it.
Yep, it'll come to you. And I had a lady asked me one time, she said, "You have any hobbies?" I said, "Yeah, amateur radio." "What is that?" Explain ham radio. Said, "Do you talk to other countries?" And I said, "Yes, ma'am, I do." She said, "Do you speak all those languages?" And I said, "No, ma'am, I don't. The universal language of ham radio is English." So don't worry about learning other. Guys, take care. We'll see some of you Friday over at our little informal meeting. And with other ones,
I have one last question.
All right.
I hope you haven't covered it already, but what is the history of CW? Does it stand for carrier wave?
It does.
Continuous.
It does.
I
And
see.
and the history of it, like I say, they call the signal that brings it the carrier wave, and CW is a continuous wave, and
Oh, it stands for continuous wave?
and because what a CW signal is the same thing over and over and over and over and over. It's that oscillation over and over and over and over, and that's really what the CW means. But it also means Morse code, because what's used when you turn that CW on and off is code. Used for both, but it is, yes, wave.
Okay.
So, well, and it's just because that's what you use is that carrier wave, and you're turning it on and off for CW.
Okay. Thank you, sir. Thank you.
Certainly. And you don't have to learn it to get your license anymore.
That's the good news.
Well, you can ask Zach. Zach didn't have to have it for his license either, but he found advantages to learning it. So Zach operates Morse code now. I enjoy it. I spent my Sunday on the North Carolina QSO party. A QSO was the conversation. So it's a North Carolina QSO party, which is every state seems to have one. And you contact as many different people in the state, and quite a few of mine were on CW, and some of them were on phone. And I enjoyed using both of them during the weekend. It's just, I'll admit, when I was a kid, that's one of the things that got me. Says, I can learn something that nobody else will understand. So I guess I was a funny kid, but that's the way things were.
Oh, okay. Well, thank you once again, and please have a great evening. Thank you.
All right, you're welcome. I will. I'll talk to you in a minute, Chris.
Okay.
And I'm going to leave for all.
You gonna turn off the recording?